Okay, can you guys hear me? Is good? Right. Welcome everyone to our second lecture on GANs. So the few of you here and the people on Zoom. This lecture is going to be taken by me. I'm Aditya, your TA, and our fellow TA is Shreyas and Talha, who should be arriving. Um, right, let's get into it. So yeah, topics for the week. We've been looking at GANs. We saw VEs last week, and on Friday there was a lecture on GANs. I hope you were there. And we're going to be continuing with GANs today. So the agenda for today is that we will do a quick recap of GANs, and then we will go over the GAN training routine and look at some of the common issues that arise when one trains a GAN, followed by the remedies of such issues. And towards the end, we will also look at some of the latest architectures in GANs and where the research is currently headed. So to recap, we saw that discriminative models learn a conditional probability, which is what most of this course has been about and what your homeworks have been about. But we can also have a generative model, which learns the joint distribution P of X and Y, and they can learn the distribution of the training data itself. That's P of X using the Bayes rule. And what's good about them is that they can do both discriminative and generative tasks, and they are nowadays commonly used for their generative capabilities. So let's recap the problem as well. The problem was that from a large collection of images of faces, can we have a network that can learn to generate a new portrait? Can we generate new samples from the distribution of face images? So yeah, to rephrase it, given a data set, how can we generate more points like it? And we've seen a couple of approaches to this question. So would anyone like to enlighten me as to what approaches we've taken to this problem? Anyone here or anyone on Zoom?
Sorry. So there's the autoencoder way.
Sorry?
There's an autoencoder way.
Autoencoder? Yeah, exactly.
A decoder.
Yeah, exactly.
How's the variational autoencoder?
Yeah, but what it actually does is, so that's the autoencoder way. We approximately model P of X, and we then sample from it. Once we know P of X, we can sample from it. So we define some tractable likelihood function and approximate P of X using our data set. And then we can sample from this distribution. And we do this using maximum likelihood estimation. And we discussed some issues with that, as it does not directly concern with whether the sampled point actually comes from the distribution of faces. So in the face image example, we find the function such that the probability of the face images is maximized, and we hope that it learns to generalize to generation. But we could just as well end up with a distribution which just assigns high probability to the training samples and the rest is garbage. And as a result, oftentimes the produced images are blurry. And the other approach that we just saw in the last class was that we can model an approximate sampling function of X, which is not P of X itself. And so we can just as well learn an implicit model, which does not specify the distribution of the data itself, but rather defines a process which after training aims to draw samples from the underlying data distribution. And the generator can be trained in this adversarial manner to produce much sharper results. Any other ways in which we can approach this? So the third one, which we will not be covering, but I'm sure you've heard about them. Diffusion models do something else entirely by repeatedly adding noise to an image and then learning to recover the input. And intuitively, they try to learn how changing a data point X changes its likelihood of being observed. And that has really nice results that I'm sure you guys have seen all over the internet. So coming back to GANs, here's a general framework of GANs that we've seen. We have a generator which samples from a random noise distribution, which generates fake images, and it tries to make them as close as possible to the real data. And we have a discriminator, which is a binary classifier telling us whether an image is real or fake. And the purpose of having this discriminator is so that we can measure how well our generator is doing and improve it. So we can see that our discriminator needs to be somewhat good at its job. Otherwise, there's suboptimal feedback for the generator. And the ultimate goal for the generator is to generate images to fool the discriminator. And for the discriminator is to find out which images are real and which are fake. So we see that the generator and discriminator are always fighting against each other. So if you do it for images, then your GAN would look something like this, where you have some convolution layers. And once trained, you can generate new images, generate new text, and even generate music. So yeah, now we can see an example of what GANs can do. We'll just
Let's try and darken that up a bit with some cloud. Oh, that's wonderful. What if we were to change all that to rock?
Okay, let's click on rock and we gotta replace the mountain.
Let's try waterfall just by pulling water down from the top there.
Okay.
Wouldn't it be great if everybody could be an artist? If we could take.
All right, we can come back to it later. But yeah, that's what GANs can do, and a lot of other domains as well. So now let's look at the GANs training routine. But before we get into training, let's establish some notation. The training data is denoted by a vector x, which is what the generator is trying to resemble. And the noise vector that the generator will sample from is z, which is usually from some normal or uniform distribution. And the discriminator and the generator are both some class of neural networks, as we saw earlier. And they're parameterized by theta d and theta g. And the discriminator takes in an image and gives the decision of real or fake. Here we indicate the real images with label 1 and fake images with 0. And the probability distribution of the real data is p of data, or p of x. And the probability distribution of the generator made fake images and the latent noise vector are p of g and p of z respectively. The generator output will be denoted by g of z, and it will take in the latent noise vector and give us an image. And the discriminator output for fake data will be d of g of z. And for the real data, it's d of x. Okay, so hopefully this equation is familiar to you all by now. We saw how the discriminator was trying to minimize the binary cross entropy loss between the real and the fake targets. It's just a binary classifier, so that it can correctly classify real as real and fake as fake. And that's equivalent to maximizing the negative of the binary cross entropy, which turns out to be this guy. And if we consider the latent vector z, then this equation would look like this. But the objective of the generator is to fool the discriminator and sort of prevent it from being a perfect classifier. So it tries to minimize the same term, working with feedback from the discriminator to improve. And in this equation, the generator really only affects the second term that corresponds to the fake data. And the first term corresponds to the real data. So now we'll break it down. So we have the discriminator, and the discriminator's objective is to maximize the output for the real data, take it as close to 1 as possible. And yeah, keep in mind the real data is label 1 and fake is 0. And it also wants to minimize the output for the fake data, so take it to 0, which is the same as maximizing 1 minus d of g of z. The objective of the generator is the exact opposite. It wants to maximize the output for fake data. It wants the discriminator to output 1 for the fake data, and that is just then minimizing the 1 minus d of g of z term. So we can take a log over these objectives. It makes the math easier. And so for a single data point, we want a discriminator to maximize the log over output for real images and log over output for fake images. And the generator objective is trying to minimize the second half of the equation, which is to maximize the output of the discriminator over the fake image. So to make the discriminator output that the fake image is real. And that's for one data point. And if we do the same over the entire distribution, we take an integral over it and we get the expectation, which is similar to the empirical risk stuff we've been doing since the first lecture. So we get our original objective that we saw a few slides ago. So now we have our entire GAN objective. The discriminator tries to maximize it, the generator tries to minimize it. And as you must remember, in practice, it's difficult to simultaneously optimize this min-max objective. So it's done in a stepwise way, in 2 steps. And the math also turns out to be much simpler that way. So we first optimize our discriminator, and once we have the optimal discriminator for that pass, we will use that to optimize for the generator. So we can take a derivative of our objective with our discriminator, and we can find the optimal discriminator at that point. And we derive this as p of x divided by p of x plus pg of x. And once we have this, we have performed our inside maximization objective over the discriminator. And once we have this optimal discriminator, we can plug it back in and perform minimization over the generator. And as we saw, as a result of this two-step process, our generator objective comes out to be in terms of this Jensen-Shannon divergence, which has some nice properties over the KL divergence that we will be exploring throughout this lecture. So yeah, this is the algorithm cited from the original GAN's paper, like we discussed. We first optimize for discriminator by passing in real and fake images, by sampling from the latent noise distribution, and then we optimize for the generator. And now we have a poll. All right, 20 seconds. But before we discuss the answers. All right, 10 seconds, guys. So what's the answer? Anyone?
2 and 3.
Sorry?
1, 2, and 3.
Yeah, that's correct. All of them are correct. So yeah, the generator objective looks like this if you have the optimal discriminator. And the JS divergence between two distributions is always non-negative and only 0 when two distributions are equal. So all of them are true. And yeah, these are two theorems from the original paper. The global minima of L is only achieved if and only if P of X is equal to P of G. And at that point, the objective is negative log 4, and the discriminator is unable to differentiate and is just randomly guessing. Another theorem is that if the generator and discriminator have enough capacity, and we train this in this two-step process by first getting an optimal discriminator and then using that to optimize for the generator, then P of G converges to the data distribution. So you can find proofs for these in the appendix. So now let's look at some qualitative effects of the JS divergence. And we saw that our generator objective was reduced to a Jensen-Shannon divergence. So what does that provide us with? As opposed to the KL, the JS divergence is symmetrical in nature. And before GANs, we had networks trained with KL divergence, generative networks. And by nature, they preferred diversity over realistic images. So they produced a diverse variety of data, but it was not close to the original data distribution. And we can see why that happened. So on the left graph, we have P, which is the data distribution, and Q is the generator distribution. And on the graph on the right, we see the penalties. So we see that for values x greater than 2, the penalty is very low, which means that diverse images, but images that do not fall under the data distribution, would still pass through the generator and not get a heavy penalty. So overall, we would get poor quality of images, but a more diverse set of samples. And the JS divergence, on the other hand, is symmetrical, and it allows for less diversity, but heavily penalizes poor images. So we can see that when P of X is 0, there is still a high penalty. So the generator part trained using JS divergence will produce high quality images, which resemble the original training data, but we will often see less diversity. And there are some exceptions to this, so I will refer you to the blog and the original paper to read about those. So we looked at the GAN training routine in a gist, and we saw the advantages of doing it in a two-step process. But doing this also introduces issues, and we will look at some of the issues and some remedies in brief. So the first one is mode collapse, which we talked about a little bit in the last lecture. So as we saw for JS divergence, it optimizes for realistic images, but not for diversity in images, as it penalizes diversity heavily as well. So there is a risk of the generator generating just one output or a small range of outputs that keep fooling the discriminator over and over again without actually really being different. And how it happens is that we know that the objective of the generator is to create images that can fool the discriminator the most. But in the extreme case, the generator can converge to find one optimal image, say X star, that fools the discriminator the most. And for the discriminator, that is the most realistic images. So in this case, X star becomes independent of the latent noise vector Z. And for the discriminator now, the most effective way to detect generated images is to just detect this single mode. So the generator then looks for the next most vulnerable mode. And so both networks just get overfitted to exploit these short-term opponent weaknesses, leading to the model not converging. And we can see that visualized in the figure here. So you can see in the first row, your generator actually generalizes to the target distribution. And in the second row, it just bounces around from one point to another and doesn't actually care about producing diverse outputs. And yeah, in images, it might look something like this. So total mode collapse would be when the generator continues to generate just one image, but that's rarely seen in practice. And partial mode collapse, something of this sort, is much more common when there is a limited variety of generator outputs that fool the discriminator continuously. So in this figure, images with the lines of the same color are just variants of the same face with different properties, like tint or brightness. So another issue is vanishing gradients. So let's say our discriminator gets initialized to a very good point to correctly classify fake images in the first pass. In that case, it will provide no feedback to the generator, and there is no gradient to optimize the generator. So we can see that through this representation. So in the figure on the left, P is the data distribution, and Q1, Q2, Q3 are the fake distributions. They're all Gaussian distributions, and on the x-axis, we have the mean of the Gaussians. So on the plot on the right, we plot the GS divergence between the distributions as the distance between P and Q increases. And we see that the gradient for the GS divergence vanishes from Q1 to Q3. So the GAN generator will learn extremely slow or nothing when the cost is saturated in those regions. And this is one of the reasons why currently there's a lot of research being done around cost functions for GANs. And we can see a similar situation when the discriminator is not good at all. So ideally, we want the discriminator to be not too good too early or stay too bad for too long. And yeah, this behavior of the discriminator being too good happens especially early in training. So for people doing homework 5, you'll see that it takes a lot of epochs to even observe a marginal change in your model. So just be patient. Right, so one of the most common training issues is convergence and oscillation. So because of the adversarial nature of GANs, in a game theoretic sense, it is a zero-sum non-cooperative game where the generator and the discriminator are always in competition. And deriving from game theories, the system will always converge to the Nash equilibrium. Yeah, does anyone know what the Nash equilibrium is? Go for it.
So each operand doesn't have any better rules for each other. So that is the best rule for each other.
That's correct, yeah. So it doesn't change the expected outcome, no move. So it's a situation where each player chooses a strategy such that no player can increase their expected payoff by changing their own strategy. And in a GAN, Nash equilibrium can be defined as a situation where no matter what changes in the generator and the discriminator, the output of the system will not change. So we can understand that like this issue through a simplified example. So consider this scenario where there are two players, A and B, that control the value of X and Y respectively. And player A wants to maximize the value XY, while B wants to minimize it. So we can also say that B wants to maximize the negative of XY. So f of X is the objective of player A trying to maximize XY, and f of Y is the objective of player B trying to maximize the minus of XY. So if we were to take gradients of these functions with respect to X and Y, and take a learning rate and apply the gradient update, can someone try and guess what the Nash equilibrium would be in this case? Anyone Zoom?
0 maybe?
Yeah, that's correct. Whoever that was, good job. So yeah, the Nash equilibrium would be a situation where the multiplication of x and y would not change. So the equilibrium would be x is equal to 0 and y is equal to 0. And this is the only state in which your opponent's action will not alter the expected outcome. So yeah, x is equal to 0 and y is equal to 0 is the solution that we hope gradient descent would lead us to. But in practice, we find that it does not. So if we see the plot of xy and xy, the multiplication of xy, and how they vary after many iterations of gradient descent, we see that it keeps oscillating and never really converges to x and y equal to 0. And this is a very real problem with training GANs and in general any min-max objective, as the parameters keep oscillating and never converge to the Nash equilibrium optimum. And intuitively, this can be viewed as for every move you make, your opponent countermeasures your moves, making the model harder to converge. So now we're going to look at some remedies to these problems. Any questions until now? Okay, so the first technique we're going to look at is feature matching, which is mainly used to combat the convergence issue and also reduce mode collapse. So we talked about mode collapse. It happens when the generator overfits to produce similar outputs, but we want to make our generator output more diverse. So we want to learn better statistics of the data distribution to make the generated distribution more close to the real one. So we make the generator produce a multi-dimensional output, which is the statistics of the data itself, instead of just a simple 0-1 label. And we also change the objective function correspondingly to an L2 distance between the generated image statistics and the real one. And in practice, an effective way to do this is by extracting the feature embeddings from the discriminator and using that to calculate the L2 distance or some other distance. And in the original implementation, they suggest that the generator should be trained to match the expected value of the features on an intermediate layer of the discriminator. And this is a natural choice of statistics for the generator to match, since by training the discriminator, we are asking it to find those features that are most discriminative of the real data versus the generated data by the current model. Another technique to tackle mode collapse is called mini-batch discrimination. And how it works is, while passing in a batch of data to the discriminator, we actually append a similarity score to one of the feature embeddings in the discriminator structure. And this score is computed over the entire mini-batch. And so the intuition is that providing the discriminator with information about data in the entire mini-batch will make modal collapse easier to spot. As if the generator generates faces from a limited variety, then the similarity score will be high, and the discriminator can use the score to infer whether the batch is from the real data or the generator. So how we do this is shown in this figure. We get some feature embeddings from the input, and we apply a transformation over it and map it to a high dimensional space. And I think intuitively we do that to better calculate the distance. And after we get the matrices after the transformation, we calculate the pairwise distance with all of the samples in the mini batch. And we add them up to use as our similarity score, which is concatenated to the input, the feature embeddings. And there are also some other ways to do this. So instead of similarity scores, we can do a similar thing using the standard deviation. But the general idea is that you can attach some statistics feature map to the feature map in the discriminator. Some state-of-the-art GANs also include style information and other content information to get better control over the images being generated. Another trick is historical averaging, and it is used to combat the oscillation issue. So we keep a moving average of the historical parameters in the last few time steps, and we add this new term, the L2 error, to the loss to punish the model if the updated parameters move too far away from the historical parameters. And for GANs, this can stop the model from circling around the equilibrium, like we saw in the earlier example. And so it can act as a damping force. We can also use label smoothing to prevent our discriminator from being overconfident and increase the calibration of our model. And by now, I think all of you may have used label smoothing in your homeworks or other research. And as you know, we have some sigmoid or softmax layer at the end of our model structure to map our hidden states into probabilities. So since our model is basically zeros and ones, the sigmoids or softmax try to saturate to those two values. But we don't want our model to be too confident about the training results. And we'd rather it be less confident in training, but perform better during evaluation. So we smooth the zeros to epsilon and the 1 to 1 minus epsilon. And yeah, or the 0 in the sigma, the 0 to 0.1, 1 to 0.9. But in GANs, in practice, actually we do one-sided label smoothing, which means we only smooth the real targets, but still keep the generated targets. So why we do that is, if we smooth both the real and generated targets, and we replace the positive target with some alpha and the negative target with a beta, we would get the optimal discriminator to be this guy here, alpha p data x plus beta p model x by p data x plus p model x. So can anyone spot a problem with this discriminator? Anyone on Zoom? Shreyas?
Yeah.
Anyone on Zoom? Any answers on Zoom?
Maybe multiple matching.
Sorry?
Multiple matching covariance.
Sorry, I can't hear you.
Multiple matching covariance, would that be the problem?
Oh, no, not really. And the equilibrium would stay the same. That wouldn't change. Okay. So actually what's problematic here is the presence of this P model term in the numerator, because this is the only difference from the earlier discriminator we had without label smoothing. And you can think about it, because in areas where the probability of data is approximately 0, but the probability of the model is large, erroneous samples from the model, the generator, will have lesser incentive to move nearer to the data. As in those cases, we would want d of x to be low, but it would still be close to 1, which is the label for reals. So we only smooth the positive labels to alpha, leaving the negative labels set to 0. Does that make sense? Cool. So the final technique is virtual batch normalization. It is used to accelerate convergence like batch norm, but training is done a bit differently. And why we do this is that batch norm causes the output of a neural network for an input X to be highly dependent on the other inputs in the mini batch, as the statistics are derived from the mini batch itself. And that can lead to images, the generator generating images like this, where we can see that there's the same color tint in the batch, and yeah, in outputs from the same batch. And this bias even overwhelms the randomness of the latent vector Z. So instead of using batch information for each batch in the training process, we fix a batch by manually selecting a batch of real data at the beginning of training, and we just fix it during the training process. So we use this reference batch to do batch normalization while training the generator. And we can choose any batch as long as it stays constant. I think in the default, from the original implementation, the first batch is chosen. And this gives a more diverse generated output and also accelerates convergence. So I urge you all to experiment with these tricks in homework 5. And now Shreyas will introduce us to some other state-of-the-art distance functions. Shreyas? Do I keep this? Put it in pocket.
Hello. Yeah, so in the last lecture, we've seen that VAs use scale divergence. We use scale divergence with VAs for training, and we use Jensen-Shannon divergence for training GANs, right? So let's consider a special case here. So we can see there are two distributions here, P and Q. So these are two peak distributions. So the value of Px is 1 when x equal to 0, and the value of Qx is 1 when x equal to 1. So these are non-overlapping distributions. Can someone tell me what the issue with scale divergence will be in this case? If we calculate the scale divergence between P and Q, what the issue will be? Anyone on Zoom?
Not yet.
No? Okay.
Have log 0. That's what it is.
Yeah, so that's one case. So in this case, you can see that if with this distribution, P and Q are non-overlapping. So if we define theta as the distance between these two peaks, and the two peaks of the distribution, then if theta is not equal to 0, which means that they're completely non-overlapping, if we calculate the KL divergence in that case, it blows to infinity. But if we try and move these distributions close to each other, then the KL divergence drops to 0. So in this case, the KL divergence is not differentiable with respect to theta. That's the issue with KL divergence, which Abu and Aparajit also discussed in the last lecture. So that's why we use Jensen-Shannon divergence while training GANs. In this case, we calculate the mean distribution using those two distributions. So that's given by mx. And then we calculate the Jensen-Shannon divergence using by calculating the KL divergence between each of those distributions and the mean distribution. The formula is given here. And now in this case, if the distance between the two distributions is not equal to 0, we can see that the Jensen-Shannon divergence is log 2. It's a constant. It doesn't blow up to infinity. So this resolves the KL divergence issue. But if theta is equal to 0, then JSD also drops to 0. So we can see that when theta is not equal to 0, the value of JSD is still constant. So JSD is also not differentiable with respect to theta. So in order to eliminate this problem, we use a thing called Wasserstein distance. It's also known as Kantorovich-Rubinstein metric. So it's basically a distance function that is defined between probability functions on a given metric space. This can be any metric space, just say M. And so if you consider two distributions where each distribution is a pile of dirt, it consists of points which are just like, it's just a pile of dirt. So what's the minimum cost of transforming one pile of dirt into another? That's what Wasserstein distance is. So it's basically the amount of dirt that you need to transform multiplied by the distance, the mean distance by which it has to be moved. That's the Wasserstein distance. And so in this figure, you can see that the red points show one distribution and the blue points show the other distribution. And yeah, so there can be a lot of paths from one distribution to the other, but the optimal one is the Wasserstein distance. So back to our first example, back to our special case, we can see that the Wasserstein distance is just the value of theta here. Now it is differentiable. And yeah, so the Wasserstein distance is given by this formula at the top, but we can see that this formula is like intractable. So we can do a bunch of math and arrive at this min-max formulation. And in order to satisfy this duality, the KR duality, we need to have a different kind of a discriminator function for a function that is different than vanilla GANs, than normal GANs. So in this case, dx should be a one Lipschitz function. So what is a Lipschitz function? A Lipschitz function basically ensures that the Wasserstein distance function is continuous everywhere and differentiable almost everywhere, which is what we need. And so also a function is k Lipschitz if its gradients are at most k everywhere. So, and yeah, so in the original paper for Wasserstein GAN, they achieved this condition by a trick called weight clipping. They restricted the weights from a range of -c to +c, and c is a hyperparameter here. So any of you people who are working on homework 5, tuning this hyperparameter can be an issue because if it's too low, then your gradients might drop to 0, which is the vanishing gradients problem. And if it's too high, then your gradients might explode. So you need to take care of that. And the next thing is gradient penalty. So gradient penalty is it's basically a softer version of weight clipping. In this case, we can see that there's an L2 norm here, and it just ensures that the training is more stable, and it requires very less hyperparameter tuning because you don't have another hyperparameter C to tune here. So it's much easier to do it this way. And yeah, so let's move on to GAN architectures. So there are many variations of GANs for modeling different tasks, but you've already seen vanilla GANs in the first lecture, and Aditya also explained vanilla GANs. But in this case, we'll look at other variants that are used for specific applications. The first one is conditional GAN. So a conditional, is there a question in Zoom?
No.
So conditional GANs basically models Px given Y. What does this mean? Can someone tell me? Anyone on Zoom? No? So Px, so here X is the yeah, go ahead.
So it looks like it's generating images conditioned on like some goals, some like goal what it's supposed to be like here.
Yes, exactly. So it's generating images based conditioned on the input you give it to it. So for example, if you're generating samples of MNIST dataset conditioned on the digit you are generating. So this model is constructed by adding labels Y as input to both the generator and the discriminator. So like you can train the model in such a way that if you say something like, I want a number 2 or I want a number 7, then the model will generate the same thing. That's what you're doing in this case. And this is the min-max formulation for this case. And as you remember, in vanilla GANs, we're looking into Px. And in this case, we're looking into Px given Y. So that's the only difference between vanilla GANs and conditional GANs. And why this is, so you guys remember in vanilla GANs that it can generate random images from the domain, but because the relationship between the latent space and the generated images, it's kind of difficult to map. But if you condition it on a specific input, then it just produces the things you want. You can train it that way. If you pull out the model, as a standalone model, you can just generate the images you want. Okay, so this is the architecture for a conditional GAN. You can see that in the discriminator, you have both X and Y as inputs. And in the generator, you have the latent variable Z and Y as input. So both of these adversaries get Y as the input. And these are the results from the MNIST experiment. You can also see that there are some errors here in the row where it's showing 4. Some of these are 8. So it's not perfect, but yeah, even conditional GANs can make errors. And so yeah, so the next variant is LapGAN, so which is basically Laplacian GAN. It is just a chain of conditional GANs. So it just generates progressively larger images, because you know that that a normal vanilla GAN generates small and blurry images, but a conditional GAN generates larger images conditioned on the smaller image, which is repeated until you reach the desired size. It's not recommended to go from a really small size to a really big size. You can mess up your model that way. And so this is the architecture for LapGAN. And you can see that we are dividing a big problem into smaller problems and making it easier to train a GAN model, train a conditional GAN model. Yeah, so yeah, that's my part. But before I go, there's a poll. I think I've released the poll. How much time? 10 seconds, guys. You want to take the mic?
I'm just uploading the slides.
Guys, slides should be up on Piazza now. Sorry for that.
Yeah, so time's up. The question was, the main difference between a vanilla GAN and a Wasserstein GAN is that in a Wasserstein GAN, the discriminator is restricted to have a bounded Lipschitz norm, which is true. I hope most of you answered true. Yeah, and so Tara will take it from here. The original thing.
The slides are up.
Can you hold this? Thanks.
All right. Okay, so now we'll be discussing some more specific application-specific GANs. So this is the original paper. This was developed by, this was first introduced by Ian Goodfellow in 2014, and this is what sparked like all of the trends in GANs that we see today. We've gone through this already, and so this is a representation of GANs with time. And essentially, you can see that over the years, the outputs of these different GAN models have better resolution, more clarity, and this is a trend which just keeps on going. Most models today, if you have been running inferences, you see the output images are 256 by 256 or 512 by 512. And as much as it pains us to not be able to use those for more real-world applications, this is a trend which is changing with time, and sooner rather than later, we'll have full-scale, maybe even 3D models being output by GAN networks. This is a very specific GAN application for manipulating celebrity faces. This is another one of progressively growing GANs. and this is one for high fidelity natural images. So all of these applications have papers associated with them, and I would recommend you to have a look when you get back and are reviewing the slides. But now let's jump to two of the arguably most important GAN architectures. The first one is BiGAN. All right, so this was introduced by Jeff Donahue in 2016 in their paper called Adversarial Feature Learning. So a BiGAN is a bidirectional GAN, and it has one key difference that sets it apart from like traditional conditional GANs, vanilla GANs, and the WGANs that Sheris was just talking about. So the idea is that this is the type of GAN where the generator not only maps latent samples to generated data, but also has an inverse mapping from data to the latent representation. So mapping from simple latent distributions to arbitrarily complex data distributions has been demonstrated empirically with compelling results, right? We've seen those results with time and they just keep improving. However, there could be a use case where we have where we predict these semantic latent representations given the data. So what we have been doing is going from the latent representations to the data. What if we come across a use case where we need the opposite, where we go from data to the latent representations? So this is where BiGANs come in. It has a network which does both of this together. So GANs in their existing form have like no means of learning the inverse mapping, which is projecting the data back into the latent space. And in this case, in the case of bidirectional GANs, this is a means of learning the inverse mapping. And this demonstrates features that can be used for auxiliary supervised discrimination tasks. So that's a lot of words, but let's jump into like some examples to see what it actually means. And before we get into like the results to motivate why we need BiGANs, this is the general architecture that BiGANs use. So not only do we train a generator, we additionally train an encoder E, and the encoder introduces a probability distribution P of E. And you can see that the features are mapped into the data, and then we learn both of the mapping relationships at the same time. So BiGANs share many theoretical properties of GANs, which was introduced by Ian Goodfellow in his original paper, while additionally guaranteeing that at the global optimum, G and E are each other's inverse. And BiGANs are also closely related to autoencoders, and you've already learned about them in the previous lectures. The way they're related to autoencoders is that with a zero loss function, and in the following sections, we will highlight some of the appealing properties of this kind of network. All right, so this is more pictorial representation of what's happening. You can see that latent codes go through the generator and create generated images. At the same time, those generated latent codes are being generated by dataset images from the encoder. So not only do we have a generator and discriminator, we add an additional encoder, which gives us two sets of inputs to the discriminator. One set is with a real image and a fake latent code, and the other one is with a real code and a fake image. So a BiGAN has knowledge of the regular mapping as well as the inverse mapping, and that's what makes it so useful. All right, so that was the network, but what are we doing at its core? So at the core of every neural network, there's an objective function. And in this case, we have this beast right here, right? So how many of you understand what's going on here? Maybe I can simplify it for you guys. Let's see. So in this case, so the BiGAN objective is a min-max objective function, but before we before we run it through an iterative algorithm which optimizes this equation that we have here, let's try to see what it actually means. So this is, so the DEG stands for discriminator, encoder, and generator. And this has two parts. So the first part is the expectation of X. log D, and this is the expectation. So wait, actually, this is incorrect. We have X and the output of the encoder when X is passed into it. This plus the Z value, again, expectation, yep, log 1 minus dx, and this goes to the generator. And there should be another bracket. Yeah, hopefully this is a much simpler representation than what we have right here. Wait, actually, there's a mistake in this. Can any of you identify it? Any takers on Zoom? No? Okay, so actually, yeah, go ahead.
I don't know. I feel kind of guilty because like it says in the slide like what it's supposed to be. So on the right there's like log 1 minus z.
Oh, so that is one way to represent this entire part. So it doesn't have to be dxz, but both of these should be, oh, I'm sorry. Both of these should be z's, right? Yeah, you were close enough. All right. Anyway, so when you guys go back home, it's a good practice, just to, whenever you read or come across a new GAN paper, I would recommend going through all the images first to get a sense of what's happening, and then read the equations and compare it with the code that you have. So not every time you'll have a code on GitHub or papers with code or whatever from the authors. But when you do, and when you start comparing equations in the research paper with the code that is available to you, you will develop this intuition that will help you implement the paper when the code isn't available. So it takes time, but slowly these equations will start to make sense. Anyway, so this is the fun part. This is the qualitative results for the BiGAN network that we just talked about. So what you see on the topmost section, the topmost row section are the generator samples, and every other, the bottom 3 row sections are the real data and their corresponding reconstructions. So you can see that for every input X, you have output which may not be very close to the latent sample, but it's trying to learn these mappings as it progresses. So what are the takeaways, right? So BiGANs were found to be better at feature learning than unsupervised models, and equivalent or better than some self-supervised models, which was a big thing in 2014, right? Actually, not 2014, 2016, that's when the paper came out. Another good feature about BiGANs is that they are domain agnostic. So they're very generalized models. You can pick it up and apply it to a different application. It should work really as well. And we discussed domain shift earlier, and these needn't suffer from that problem. So the core idea of BiGANs is that they can learn feature representations from unlabeled static images. And yeah, that's pretty much it. Now we go on to the next GAN architecture, which are cycle GANs. So when you come across deep learning applications in the news, on like social media, when people are talking about deep fakes or all of these hype AI results, more often than not, it's just cycle GAN in play. And what's happening here is actually just a feature of the cycle consistency loss. There is more at play, but when Professor Jun Yanzu came out with this paper in 2017, in his paper, Unpaired Image-to-Image Translation Using Cycle-Consistent Adversarial Networks, he proposed 2 pairs of GANs. So you train a pair of conditional GANs to perform image-to-image translation. So the first GAN is trained to convert an image X to Y, and the next one is trained to convert an image Y to X. So you have two classes, and you're trying to convert one class to the other. And he also included a loss function, which had an additional cycle consistency loss. And we'll get into that in just a second. That kind of changed the game in this space. Also, Professor Junian was at Berkeley at the time, but now he's a professor at CMU. He also has a very good course called VLR, which was fun. Yeah, but very time consuming, but anyway. All right, so before we get into the equations and everything, these are some of the results of cycle GANs. You can see that you can really convert one class of image to another. So you have regular pictures. Let's look at that example on the left, top left. So you have paintings from Monet, and then you want to convert it into like regular pictures. You have a class of images and another class of images, and you're trying to convert it into each other. And similarly, you can do it for like different use cases. If you want to convert a stylistic painting into a different one, from one animal into another, seasons between each other. And we'll just focus on the central example right now, the ones with zebra and horses, because there are a lot of edge cases that we can really talk about. But any questions at this point, up to this point? You guys understand what this is doing, right? Okay, great. Okay, so in the cycle GAN architecture, you have a set of classes that go from, say, in this case, we have a horse and a zebra, right? So you'll have two different cases. One in which the horse is being converted into a zebra, and another in which the zebra is converted into a horse. And both of these will be related with the cycle consistency loss. And what you see at the bottom is at the core of what's happening. So we have two mapping functions, G, which maps X to Y, and F, which would also be the same case for F, for which maps it from Y to X. And for both of these cases, there are two losses. One is the adversarial loss, and the other one is the cycle consistency loss. And both of them sum together make the total loss. And the idea is that dy encourages G, which is the generator, to translate X into its outputs, indistinguishable from the domain. And it happens the same way for the other class as well. And we also add some regularizations, and with the help of the loss function, we're able to get the training objective. All right, so again, back to the equations. Every neural network has a training objective, and this is how we define the loss in this case. So we have an adversarial loss and a cycle consistency loss. You guys are familiar with the adversarial loss, but the idea is that the adversarial loss is used for matching the distribution of generated images to the data distribution in the target domain, and the cycle consistency losses prevent the learned mappings G and F, so G and F from contradicting each other. And these are the two different cases that we have. When we combine both of these together, we get the full objective. And then we, again, aim to solve this argmin function that we have, the min-max function that we have. Okay, some cool examples before we get bogged down in the equations. So this is a very relevant and real-world use case of cycle GANs. So you must have come across satellite imagery of the sort on the left side. What if we could train a model which gave us the mapping we needed to convert that satellite imaging into a cost map, essentially, or a vector representation of the map that can be used for self-driving, right? And this is exactly what Google Maps does. Also, now imagine if you have these maps for like a certain area of this certain part of the city, but you wanted to see what it would look like from a satellite view. So training it with a cycle GAN would give you both the mappings to convert those type of satellite imagery to vector maps, and convert vector maps to satellite imagery in case you happen to need it. Anyway, this is a cool example which is used, and I'm sure a lot of you have used this app before, so you know how you get these maps now. A second example, and this is actually from my own research, is converting daytime images to nighttime images and nighttime images to daytime images. So we have input a stereo pair of images into the model, and we have rendered the daytime images. And the way you do it is you have a set of nighttime images and a set of daytime images, and you're trying to make the model learn how to convert daytime images into nighttime and nighttime into daytime. And yeah, once you have those mappings, what you can do is you can apply that to the test data set and convert nighttime images into daytime. Yeah, and this has very real world benefits because for one, there is a very inherent bias in most data sets today. Most of these data sets have images which are well illuminated. Most of these images have been taken in the day because of logistical reasons. And because of that, most of these pre-trained models or self-driving algorithms that we have are biased towards performing better in the day. However, if we have something like this, we could convert all of those training images, which are daytime images, to nighttime images and train our models on those nighttime images and perhaps get similar or close enough results. And yeah, so nighttime images also lack a lot of features. So when you convert those nighttime images into daytime images, you get a lot more features and you get a better ground truth. So that stereo pair, when input and extracted as the daytime pair, what you could do is you can get a stereo output. It's a little dark, but for localization mapping, that's more than enough. This is also the entropy output. And yeah, that's about it. Okay, so what are the takeaways? So cycle GAN is particularly helpful when paired training data is unavailable. So perhaps you have a data set of humans and their edges, right? And if you want to convert one type to another, it's very easy because you have both of those annotated data available to you. However, in cases when you don't really have examples like this one, right? Like, when are you going to come across a data set which is a one-to-one mapping of zebras to horses? That's not going to happen. So in those cases, cycle GAN is very helpful. And it also has some caveats. It doesn't come without them. One of the edge cases is if that the test image is very different from the similarly input training image, like in the case of the horse. So we have a horse here and we want to convert it into a zebra. However, because this image is not very close to what we have input into the data set, the output of the cycle GAN is going to be a very weird output, which to the algorithm probably makes sense, but to us, we know that that's probably not very accurate. Who knows? Again, so this paper was succeeded by another paper by Professor Junia, and it's called Contrastive Unpaired Translation. And it's essentially an unpaired image-to-image translation model that enables fast and better, like more memory-efficient training. Look it up, yeah, it's pretty helpful. So cycle GAN is a very commonly used GAN architecture, and it has some offshoots that have evolved into categories of their own. One notable category is neural style transfer. And this is an optimization technique used to take two images, a content image and a style image, and then it outputs a novel image which has the content of the first one and the style of the second one. It essentially blends them together. This was also extended by NVIDIA into what they call style GAN, and it has variations and versions. So I think this is closely related to style GAN 1. And the idea is if you put in an image of a dog, which is the content, and a style, you should be able to get an output which is of a dog painted in this styling format. And yeah, I'm sure you must have seen results like this before. Now you know how to get it done. And there are a lot more applications of this where you can use it for image and painting or deblurring, etc. Again, I won't dwell too much on this, but it's important to know that the objective function has two main parameters. One is the content loss, and the other is the style loss. So again, just a quick recap. What you see on the top left, the object you want to change into the different style is the content and the style. And we'll use this nomenclature in the objective function. So the content loss is based on the intuition that images with similar content will have similar representation in the higher layers of the network. And the probability of Lij is the representation of the original image, and f of Lij is the representation of the generated image in the feature maps over the layer. Again, so this is incomplete without the style loss because we have both of those elements in this network. Again, you should be able to see the similarity between this model and the cycle GAN model because there's two things at play. But again, it's not just the vanilla cycle GAN, it has its own elements, its own loss functions too. But the style loss is a representation of the original image in the representation of the generated image. So what we're trying to do is capture brush strokes, patterns, and for those reasons, we try to use some of the lower layers. So as we go deeper into the network, we get more sharper parameters, sharper features. So we try to use more of the lower layers so we can capture more of the low-level features. And that is what we need essentially to replicate the styling that we saw for the dog example before this. And yeah, we then combine both of them to get the total loss. In this case, alpha and beta are the weights corresponding to content and style respectively, and they can be tweaked according to what you want to alter the final result. Anyway, important distinctions between neural style transfer and cycle GAN. So neural style transfer needs a content and a style image, right? And this is different from cycle GAN because in cycle GAN, you just need two domains of images. You don't need to map or connect one style image with one content image. You could just give it a class of images and another class of images, and it's just going to learn the latent representation between both of those. And in neural style transfer, we have more control because you're able to essentially guide the model into styling a specific content image into the output that you would like. In cycle GAN, that's not necessarily the case. You get a more generalized representation. But again, in cycle GAN, the specificity of images doesn't really matter. It can just be a general class and another general class, a daytime image class and a nighttime image class, and you just convert it. This is let's see if I can, yeah, perfect. So this is, I'm not sure if you can see this, but let's see. Can we share this link?
I'm not sure. It's a different browser.
Okay, it's fine. There is a hidden slide on the slides. You can go ahead and play around with it, and hopefully that should give you a better intuition of what's happening. Also, can you get me back this slide? I think there's one slide left, but I can't see it. Maybe this.
Wait, this is a browser?
Yeah, I clicked on the link. Anyway, there's just one slide left, and the last slide essentially warns the user to pay attention to images for a few seconds every time you see them, because you never know when an image is real or if it's been generated by a GAN network. So yeah, that's pretty much it about GANs. Today we learned about different types of networks. We also learned application-specific GAN architectures. We learned loss functions, and we saw some examples of how we can use them in our day-to-day life. Oh yeah, perfect. So this is what I was trying to show you. Thanks. But I'll have to also play around with it, right? Let's see if I can do Okay, the idea is this web page is linked to the lecture slides, and you should be able to change the input image and the styling image. So the content image will be altered according to the styling that you choose. And then you can also choose the strength, which is essentially the alpha and the beta parameters that I talked about in the objective function. And you will get an output right about here. I don't know how to navigate this right now, but that's the idea. Oh, perfect.
It takes time.
Not too long. Register it. It's like 10 seconds.
Yeah, that's it. Yeah, so play around with it. It's fun to just see what's possible, but that's pretty much it. If you guys have any questions, now is the time. All right.
Yeah, I just want to end by echoing the words of a former TA. Ian Goodfellow coded up and thought of GANs after coming back from a bar one night. So anything is possible, and make sure you give homework 5 a fair shot.
Very wise words indeed. Right, are there any questions on Zoom? No? Okay. We can probably stop the recording here. And